behalf of the College of Engineering and the Department of Electrical Engineering and Computer Science, I'd like to welcome you to this seminar. Our speaker today is Don Knuth, who is probably best known to you as a result of his writings, his series of books, The Art of Computer Programming, and of course as a step in preparing an infrastructure for producing such books, he took some time out to do tech, which is widely used here, as is the case at many other leading universities. Don Knuth is the Fletcher Jones Professor, Department of Computer Science at Stanford University, and he'll be speaking today on some work entitled Experiments with Digital Halftones. Don?
First question. Well, I'm certainly enjoying today very much. I've had wonderful tours of different parts of the campus here, and also glad to see so many of you here. Hope you aren't going to be disappointed if my talk is lightweight or something. I think there's some, anyway, or inconclusive, because it's called Experiments with Digital Halftones, and I found out this morning as I went to the music lab that there was a little ambiguity as to whether or not I was talking about musical halftones or printers halftones. Now, I'm sorry about, we didn't want to resolve the ambiguity ahead of time because I wanted to get as big an audience as possible. But if you're here from the music department, I'm sorry. If you're here from the graphic arts department, it's going to be a lot more close to this. If I had said digital quarter tones, maybe this would have been more for music. But I'm going to be talking about some of the things that go into making images, and as you see, as I get into it, this is work that's in progress. In fact, what happened is that I came up with an idea last December that seemed that it might be promising. So I wrote it up, submitted it for publication to ACM Transactions on Graphics, and I wrote a paper that was tried to put into the format of the ACM Transactions on Graphics, but I had to call it the Maybe Transactions on Graphics because it was just submitted for publication. Well, just last week, just the day before I left on this trip, I got the referee reports for the article, and they decided yes, they'll accept it for publication, but I didn't know about 6 other things in the literature that are relevant to the paper. So I read those over the weekend, and that gave some more ideas. And so as soon as I get back home, I have to try some more things, and I'll try to explain what the statement of the whole thing is as I go on. Now the main problem that I want to talk about is we have a picture, and the picture is given to us in as a large matrix of values. You can call it matrix A, and we try to convert that into another matrix of the same size, B, where B is binary. So the original data is numbers between 0 and 1 continuously, representing the brightness of the picture at point ij, and we have to convert that to another binary image, either 0 or 1. Now, depending on who you talk to, 0 means white and 1 means black, or vice versa. The computer scientist or printer tends to think of 1 as where the ink goes, and a person who works with a CRT or other graphic system thinks as 1 is where the light goes, and so we get this reversal. And I'm not sure if I'll be consistent if I say black or white, but I'll probably think of 1 as being black. And those of you who prefer it the other way, I'll try not to say it so often. So I'll try to be, sort of use symmetric language for one thing. But maybe I'll need to say 0 is white, 1 is black. I don't know. Maybe 0 is black, 1 is white. It's somehow the same problem. There's symmetry about 1/2. And the idea that we have is that we want to give the impression that when you see the binary image, you're really seeing a continuous image. And a halftone, the word halftone, as opposed to continuous tone, means that we only sort of, it's halfway between. I think this is the way the word came out, that somehow halfway between what we wish we have and what we can do, because we have only two things we can do with ink. Either ink is there or it isn't. And the problem arises on computer terminals where you have two-level displays, but it rose most notably in the printing industry, where they had either to put ink or not to put ink on parts of the page. Now, the fascinating problem is that we would like to. We now have printing equipment that can control the dots of ink with extreme accuracy. It's not at all uncommon to be able to say if in every square inch you have 1,000 by 1,000 dots, and so you have 1,000,000 dots in every square inch that you could either say put ink there or don't. And this is when you consider that when you put two different dots of ink next to each other, they might blur a little bit in there's surface tension between them and so on, that they'll join together and make them larger blobs and so on, smooth each other out. Then ink will do interesting things, but these little the little variations, due to the fact that it still is little dots, are too small for the human eye to see. At that, we can control the printers now to things that the human eye can't perceive. Our laser printers are somewhere in between. They're typically 300 dots in every inch instead of 1,000. And for this, you can our eyes are good enough to detect the jagginess between. If you have something that starts out and then moves down one dot and goes over, you can tend to see that. But if it's 1,000th, it's invisible. And I suppose it won't be long before we have laser printers that are also at a higher resolution, and so that these dots, we can essentially put dots on the page just about as well as you could put ink in anyway. So we have perfect control over how to set these dots. And we also think that we're pretty smart, and we have fast computers can compute the matrix B from the matrix A by thousands of conceivable algorithms. Now, the funny thing is, though, at the moment we don't know any better way to compute the matrix B than to do something that people did by analog devices long before computers were invented. And as we all know, we can go now and buy fine books of photographs at the bookstore. And these photographs will be done. If you look under with a magnifying glass, you'll see that there are little dots on the page, and that don't really have gray tones there at all. But it's all composed of either ink or not ink. Yet these photographic books look beautiful and continuous. And these methods that the printers are actually using are not computer in the best books. In fact. It's done by methods that were developed completely independently of computers. Now, somehow, it should seem to me that there must be a better way to do that if we have all the extra flexibility of controlling every little spot on the page, that we could think of a better way to do this so we can make photographs look even more true when they're printed than with the methods used by commercial printers. Yet every time mathematicians like me have gotten into this and tried to find a way to compute the way to put the ink on it, we've come up with something that doesn't look as good as the ones that are done by the old methods. Now that's kind of frustrating, because we should think that with mathematics and more powerful computers and so on, we ought to do better. In fact, our efforts always look rather tacky by comparison with the others. Now the other people have been tuning it up since 1852, when this process was invented. So they've played with it a lot, and the printers also know how to control the process. But the question that I think is pretty interesting is to try to find a matrix B that represents, in some sense, the best way to correspond to the original matrix A, which is the thing a picture that we're trying to perceive, a picture like the Mona Lisa. Now, I'll mention different models of how we can decide whether B is a good approximation to A or not. But the first one that computer scientists typically start out with is saying that we would like, if we look in the neighborhood of position ij, and we look at at the average values of the values of B there, they would be on the average something like A of ij. So if A of ij is approximately 30%, then we would like about 30% of the B's in the neighborhood of ij to be 1, and the other 70% to be 0. So the average would come out to, the average of the B's in the neighborhood of ij should be somehow like aij. That's one simple definition of what we might want to achieve. And for this, there's a method that's elegant and simple, which I'll use to show as a starting point. It has different names. Minimized average error, as some people call it, or error diffusion. More common name I think I'll use in the next draft of this paper. But Floyd and Steinberg came up with this about 72, I think it was, and they have this nice little way of marching through the matrix and computing the B's from top to bottom, left to right, the way we read the matrix. And the algorithm is, I hope you can see it there. We just go through this I and J, going through the matrix from top to bottom, left to right. Thanks, Dan. And so so if we see something that's less than a half, it tends to be closer to 0 than to 1. So we set B to 0, otherwise we set it to 1. However, we're also making an error at this point, so we record the error of aij minus bij. That's some number that says that we wish we hadn't made this error, but we've made it. And so now we distribute the error to the parts of the A array that that we haven't come across yet. And so in the next column over, we add alpha of the error, and then in the next row, I plus 1, we fill positions j, and j minus 1, j, and j plus 1 with other fractions of the error. And these extra constants, alpha, beta, gamma, delta, can be chosen so that we get a fairly nice, somehow it looks good afterwards. We try to distribute the error to some neighboring places so that if we were close, say, suppose we went down to 0, but it was about a half, so we were making a pretty big error, then one of our neighbors would probably be raised up above a half, and so we'll tend to do it. So that's the method of Floyd and Steinberg. And if you apply it to Mona Lisa, you get something like this. Now, so the method has a virtue of fairly little computation, and it does keep the average in the neighborhood of part of the picture approximately the same as the original. So I like this method because of its simplicity. I used it a couple of times to make needlepoint patterns for my wife and so on. We have some chairs at our house where we're actually still doing the needlepoint, but I did this in 1977, made the patterns, and where we have one of her and one of me and one of the two kids each, and capturing the way we looked then in a small number of bits. And so I kind of like this method, and then I came to the point where so now I was faced with another problem where we wanted to create a font for printing halftones, and we said that we would make a font with a certain number of levels of gray. For example, the idea was maybe 65 levels from 0 to 64. We would set aside 8 by 8 areas of our page, and then somebody would tell us how gray you wanted it, and you chose one of the 65 characters, and this would give you different levels of gray, and we could use this font for typesetting pictures. And we made up, we had some experiments with that, and we were able to do a reasonably good job, not matching the good photographic books for sure, but we could still understand what the pictures were afterwards. So I wrote this up, and then I said, well, now just for comparison, let me compare this picture that was produced with 8x8 blocks, and they were fairly big chunks. They weren't square. We made them round, and so they looked a little bit better anyway. But instead of doing it this way, let me compare with something else that would look better. So I said, okay, I'll use the Floyd-Steinberg method, and I'll produce on my laser printer something where I was really doing one by one dots, but by this method, which did the minimized average error. And I was shocked to find how ugly the result looked. When I did it, this is a slightly different version of Mona Lisa, but it's a similar. But a phenomenon occurred with our laser printer that it was very blotchy. You can see here there's a big, somehow the physics of the laser. The previous diagram I showed you was produced by quite a different method. This is what happens when I actually controlled each dot, each B of ij was actually saying, does the laser turn on or turn off at a particular point? And what happened was when you had a lot of black in a row, all of a sudden the laser printer would go into dark black mode, and there was something, and somehow it would, there would be, I don't know, if you could see the original, it looked like she was wearing a wig made out of spaghetti. There are other funny textures going on in here, and so it really, although this was going to be my example of what I could do, sort of the best a laser printer could do, and to try to use that as something so we could take our approximation, which was done with a font, to something which was controlled bit by bit. I didn't have a good example at all because the font method was working better. So the natural question I had to do is saying, well, suppose I wanted to get a small version of Mona Lisa. This is a fairly small picture here. What should I actually do? What would be the best way to turn on the bits on the laser printer? So I had to learn something about the way the laser printer works, and find out that with a magnifying glass, if you put down a black you set one of these little dots on, and it also has a scattering effect that affects some of the other ones, and there are weird things that happen. Sometimes if you turn on more of the dots in a laser printer, you get something that looks less bright, and there are very funny patterns that I don't totally understand, but I certainly wanted to find something that would be more acceptable than this. Another thing I was worried about was I knew of some problems that the Floyd-Steinberg method had, for example, it couldn't be done in parallel. The calculation is inherently serial. If you look at the formulas that I gave before, the value of a sub mn, the one in the lower right corner of the picture, depends. The only way you can tell whether b of mn is going to be 0 or 1, that very last one, is by going through the entire process, because it depends on all the other values. It's possible that if I change the pixel in the upper left-hand corner, it'll affect the pixel in the lower right-hand corner of the final value. So it's inherently a serial method, and it would be nicer to have a parallel method to do the calculation. Another thing we'd noticed when we did the needlepoint patterns, there seemed to be a tendency to have ghosts. That is, we noticed that when I was doing some of the earlier experiments with the method, that sometimes a person's hairline would be replicated a little bit below. You would see a trace of where black changes to white. Sort of a history effect a little bit after that, and then I realized that something like this was sort of inescapable. Suppose I apply this Floyd-Steinberg method to a matrix that starts out and all the aij's are equal, but are all to some small, very small positive value, epsilon. So imagine that all the aij's are equal to 0.0001 or something. Anyway, some small number. Well, we go through the first row and we set everything to 0. And then then all these errors are moved into the second row, so the second row now contains 2 epsilon. And the second row we set those all to 0. And so then that error will be moved down into the third row, and we'll get 3 epsilon, and so on until finally we get to a value that's a little less than a half. And then it will start to trigger that 1 will go above a half, and then the error will cause the next one to go negative. So all of a sudden we'll have many rows of zeros followed by one row that's almost where all the error has accumulated. So everybody wants to be about a half bright, and so we'll get a row of alternating white and black, and then it'll start to improve itself. But anyway, the past history of a picture can very much affect what this algorithm does. In the worst case, it doesn't happen very often, but it can happen. Well, now there's another competing method for this, but before I show you that, I might will show you one that's current here. This is 26th of May, 1987. This is done by an algorithm similar to Floyd-Steinberg, but they have more complicated way of doing it, which tends to avoid some of those distressing effects. On the other hand, I think this would actually come out to be solid black on a laser printer and look darker than it should. I don't know for sure. If you actually would put this out on a laser writer now. Now we have, but anyway, there's another widely used technique for doing this, and it's a very clever method. Invented almost the same year as the Floyd-Steinberg method, but it has some kind of a history that led to it. Anyway, here what we do is we have this magic matrix here, which has the property that as you go through 0, 1, 2, 3, 4, 5, the points stay about as far apart from previously mentioned points as possible. And if we would take a matrix that where we would like to say have 13/64ths of the pixels equal to 1 and the others equal to 0, if we'd like to distribute these 13 far apart in some way so that they wouldn't be too clumped, and therefore we'd have sort of the high frequency, the ability to get edges and things in the pattern. Well, anyway, this is considered to be an optimum pattern for that, and they have a method saying that you repeat this pattern over and over again in your given matrix. So you imagine that this is tucked in the upper left-hand corner, and then you repeat this periodically, wrapping around in rows and columns. And so for every I and j, you have I mod 8 and j mod 8 tells you where you are in this matrix, and it has a certain number associated with it. If that number is 20, then you compare to 20 and a half divided by 64. And if a of ij is greater than that, then you turn on b of ij. Otherwise, you leave it 0. You leave b of ij equals 0. And this method has the property that if you have a constant value, then you get the right average, because if the constant value is say 13/64ths, then then the 13 of these are going to, the ones from 0 to 12 are going to be turned on, and the ones the other ones are not. This method called ordered dither, for historical reasons, is an interesting way of proceeding, and I can show you what Mona Lisa looks like in that one. Okay. So Mona in that one looks looks like this. So here we've taken the picture, and everywhere we add one of these this pattern, which in some places will go to 1 only if it's very high. Other places it'll go to 1 almost everywhere, but on the average it'll go to 1 with the right probability. And this method has one advantage, that it's easy to calculate in parallel. You can calculate Bij just by plugging in only in terms of I and j. It doesn't depend on anything in the environment. Has a disadvantage that it produces this binary texture that's looks very computerish. It doesn't look at all organic, and it has a sort of a recursive binary nature to it that really reeks of computer science in a way. So you can, if you're writing if you're trying to give the feeling of high tech, and that something has been done in a very artificial way, then okay, this kind of texture would be doing. But if you're trying to publish Ansel Adams photography, you wouldn't do this. So that's what. However, there was a way to do rather a lot better with ordered dither if the data were pre-processed, and in a way that would bring out the edges. And so here's what they call crispening the edges is a nice way to improve the quality of that method, and it's another nice idea, I think. That is, let's consider the average of each pixel value, Aij bar, to be 1/9 of the of Aij itself and its 8 neighbors, by king moves in a chessboard. So we can get this number, which talks about the environment of pixel Aij, and then certainly the values of A bar have the same average as A itself. So we can now form a combination, a weighted combination of A and A bar, and we aren't changing the average of the total. Now, but we want here to emphasize the difference from the average. So we want something that's different from its neighbor to be a little whiter if it's whiter than its average, or a little blacker if it's blacker than the average. So if we compute a weighted average in which we weight negatively with opposite signs, the A bar and the A, then we're emphasizing the difference from the average. And so this gives us something where edge effects are brought out. And this formula simplifies in a neat way. If you take alpha equals 0.9, then all the fractions cancel out, and you get a very simple formula here where you take A prime, the sort of enhanced value, to be 9 times the previous value minus the sum of 8 neighbors. And this is one of many examples of the formula above. You might not want to be such an extreme thing, but this is one way to do it, and it's the one that I use here. So I show you ordered dither when we've enhanced the contrast. You see that? So now in fact, it's almost incredible that I'm doing this with just single pixels, because you can see the river in the background now, and you can see details of her fingers somewhat, and wisps of hair even to a certain extent, and her smile might have gotten a little bit broader there. Maybe she developed a mustache. That was part of the. Sometimes you might also bring out noise in your data if you enhance it or sharpen the edges too much. But anyway, this is a possibility, and so you can also apply this to the Floyd-Steinberg method, and you see what happens then in the two cases here. With if you take the data and first do this transformation, then apply the Floyd-Steinberg algorithm, you get a surprising amount of detail, even though you have to deal with zeros and ones. Now, these pictures, you have to realize that, well, I'll talk more about it later, but our eye does funny things, as well as laser printers and printing ink. All are combining to do things when we do with visual images, and these things are still imperfectly understood. Now here we get to see another thing that tends to happen in the Floyd-Steinberg method. Well, you can't see it too well, but here it seems like the part in her hair, it's somewhat straight, you tend to get patterns that look a little bit like mazes, where you have channels developing in the method. On the other hand, I want to emphasize that this contrast enhancement, this edge enhancement transformation that we made, did not change the average value of the around IJ. We still have approximately the same average value as before, because all we did was change it by a multiple of the average, and so we haven't changed the average. Okay, now I had an idea that I thought would work better than both methods. It was something that was like Floyd-Steinberg, that would do very little to the error, but it was also like the ordered dither in that it could do it in parallel. I should mention another thing about the ordered dither method, and that is that at every step we're making a comparison where we could actually make a rather large contribution to the error. We could be throwing away typically about 1/3 of a unit of brightness in either direction. On the average, you say maybe you'll throw away 1/3. I mean, you can be throwing away even more, but on the average, it's something like that, 1/4 or something. On the average, you say this will cancel out. Sometimes you'll make an error in the positive direction, sometimes in the negative direction. But in the worst case, you could make the error always the same way and get a completely distorted view. There's no error correction at all in the ordered dither method, while in the Floyd-Steinberg method, they are very careful. Whenever you make an error, the error is distributed to some neighboring place and taken into the picture. So, well, I had the idea that I'll do something else, and in the following way. Again, I use an 8x8 matrix, or some kind of repeating pattern of numbers, some magic numbers. In this case, if you follow the numbers, you'll see that they actually don't stay apart from each other the way they did before. 0, 1, then 2, 3, 4, 5, and if I look at the first numbers, say all numbers less than 20, they'll tend to form two clusters, two globs. See, I have another picture here that shows it. It's really a space-filling pattern with a zero. There will be one glob around here and one glob around here, but you wrap that around and you get this other matrix. And I break the entire picture into 64 classes of little pixels, and all of those that are, for example, class 0 would consist of this one and the ones that are 8 to its right and 8 below, and so on, all multiples of 8 in any direction apart. And consider those to be all pixels of class 0, and then class 1 is here, and class 2 and class 3, and now I have my entire picture divided into 64 classes of things. And now that's a pattern that I apply the following error correction algorithm to it. I start out, so for every class number, K is running through class numbers, and I look at all ij of that class, like first of all everything of class 0, and then everything of class 1, and so on. Now I do something similar to Floyd-Steinberg, but for all the things of a class in parallel. If it's less than a half, I set to 0, otherwise to 1, and then I calculate the error, and I distribute the error to the neighbors of pixel ij whose class numbers are greater than k. In other words, these are the neighbors that I haven't computed yet. So now sometimes the error is going to be going up, sometimes down, sometimes to the left, sometimes to the right, all the way around. I'm distributing it to 8 neighbors of 0, and then 8 neighbors of 1, and when I get to 2, I'll distribute to 7 neighbors of 2 that I haven't yet seen, and so on. So that when I get to, finally I'll get up to number 63, and there won't be any neighbors for him to distribute anything to, because he's the last one. So he's going to have to eat that error and live with it. But everybody else, 62 is also in this situation. Nobody next to him is a larger number. But up to that time, for example, 46, when I'm processing 46, I will already have processed 38, 28, 14, and 22, but I can still distribute the error of 46 to 4 neighbors who are yet to come. And so then I won't be losing very much of my pixel mass in this thing. It'll only escape at these points that have no low-class neighbors. Now we call the points with no low-class neighbors barons, and so you define a baron position as one in which all the numbers to the around it are lower class. And this matrix has two barons. Okay. Now I didn't say how I'm going to distribute the error to the neighbors, and that's so I can weight that by a certain amount. I can do this computation once and for all at the beginning. This particular computation of the weight of class ij doesn't depend on the matrix size, so it's not very expensive, considering I'm only doing it once. And then I just continue the total weight. In this particular case, I've set it up so that I will weight an orthogonal neighbor with the weight of 2 and a diagonal neighbor with a weight of 1. So, like, for example, the first case, if I'm distributing from 0, if I distribute the error among the 8 neighbors, then I count, let's see, 1, 2, 3, 4, and then 6, 8, 10, 12. So I give 2/12 of the error to each of these orthogonal neighbors and 1/12 of the error to each of the other guys. And similarly, if I have fewer than 8 neighbors, I have a certain way of weighting the error. This is the first one I tried, and it was reasonably good, so I didn't play with any other weighting schemes. The total amount of arithmetic that you're doing here is the same as in Floyd-Steinberg. That is, the number of neighbors that you have to distribute to, it goes down from 8 to 0, and on the average it's 4, which is the same number of multiplications that we were doing for the Floyd-Steinberg method. So the amount of arithmetic is the same, but it's parallel, so it can all be done by a chip. Suitably, go over to the lab and say, make me a chip that does this kind of arithmetic on. And so this was kind of fascinating just as a parallel algorithm. It's an interesting process because if you have to imagine these tiles next to each other, and one of the interesting properties of this pattern is that the last k are the same as the first k. What I mean is, if suppose that I have if I look at the pattern of coloring the black, the first 13, all numbers 0 through 12, and I compare that to the problem of to the pattern I get by coloring black all but the last 13. That would be what is it, up to 50, 0 through 50, and then I'd have 51 to 63 left over. The 51 to 63 will form a white spot, and those white spots are the same as the black spots except shifted by 4. In other words, the pattern that you get of white on black is complementary to the pattern of black on white except for a slight shift. So the neighbors, the way so if you looked at the 62, for example, the guy next to him there would be 56. And then another one over from 59, and that's a mirror image of 1, 3, 4, 7 under reflection. So there's some interesting numerical thing. But if you watch this algorithm as it works, you start out with values at 0, and then the values start going around. Some of the error from 0 starts moving to the right. Some of it goes up diagonal and so on. And some of the error from 0 is going to wind up at 62 over here. Some of it will get all the way over, I think, by an ascending path, never going down. We'll be able to get down to one of these guys down here. And it can take a long path going up and down in some somewhat interesting ways. So although the total number of arithmetic operations isn't large, the way in which these final values propagate is somewhat interesting, not exactly mind-boggling, but interesting to imagine this kind of process in parallel where things are going, the errors are going around and around, but still not interfering with each other in some sense. Okay, let's see. You want to see what the picture looks like, though, and so here are the two examples. And what happens is you see that the fact that it's a 64, that it's repeating with order 64 makes it very visible. The place where the errors are occurring does form a regular pattern. See? However, I wasn't. By the way, this is a smudge on this. This white dot here is not real. It just happened as I was making the Xerox for this slide. And this one right again is the same with the data that's been sharpened. But anyway, it makes this regular pattern. However, I knew that would happen. In fact, I wanted to choose a pattern in which in which I would get something like that because of other experiments I had made about the way our eye works. If you actually look at the beautiful book of Ansel Adams' photographs under a magnifying glass, you look at it, you'll see that it has this kind of a pattern, and that's the way they do it with the ink. And the pattern in a newspaper photograph and so on, and it turns out, for one thing, that if we make the dots completely rectangular left and right instead of at a 45-degree angle, that pattern tends to be much more noticeable to our eyes. There's something definitely present in there. Little children can't draw diagonal lines until they're several months older than when they can draw horizontal and vertical lines. And there's something about visual perception that we can notice deviations from vertical and horizontal more in a printed page than we can when things are diagonal. And I also knew that regularity was something that would tend to be modulated out by our eyes. I did an experiment once which was which came out exactly the opposite of what I had expected. I started out with I was going to try to see how red and blue make purple, and I took a red magic marker and a blue magic marker, and I drew dots. And I started out with a checkerboard so that blue and red were alternating, and then I added to every position in the picture. I added a random change. So with probability P, I would change from red to blue or blue to red. And I started out with P equals 0, so I had a perfect checkerboard. And then I would increase P to a point where when P was 1/2, I was changing with probability 1/2, so I was getting purely random combinations of red and blue dots. And then I went to P equals 1, where again it was a checkerboard except reversed. And my original idea was that when I have these checkerboards, I would look at these red and blue dots and I would say, oh, that's a checkerboard. I can see that this is a checkerboard. It doesn't look like purple. But when I saw that, when it was a random thing, my original preconceived idea was this random. My eye would blur together the random things, and I would see purple. What actually happened was, where I had the checkerboard, I saw purple. I couldn't believe that was red ink and blue ink. But when I got to the random parts, I saw islands of red surrounded by rivers of blue. Namely, my eye very much fused things that had this repeating texture that had nothing eye-catching about it. So our eyes are very quick to pick out shapes when there are shapes there, but when there isn't a shape there, like a repeating pattern, we seem to go by it. So I wasn't minding. In fact, I figured that when I would reproduce this on a laser printer, this dot would actually be a help, and a win. It would make a nice looking picture afterwards. This is not done on a laser printer. This was done very large on a phototypesetter and then reduced down with a Xerox machine. Okay, well, at least it's a different texture. There's, the ordered dither has one texture, the Floyd-Steinberg has another texture. This one has another texture, and that's at least one thing that can be said for the method. In fact, when I applied it to a laser printer, well, here you can look at all three again just to see what it looks like. The Floyd-Steinberg at the top. They all, if you go back far enough, they actually all have the same average brightness at the different points, and so except for the distortions caused by making this slide, they all, I put them all up in my office and went back about 20 feet, and they all looked about the same, except I could see more. These were sharper at the because of the enhanced contrast on the right. Well, but when I actually came to making on a laser printer, this method which I call dot diffusion was by far the winner. So those of you who are more interested in seeing halftones out of a laser printer, I'll show you the hard copy so that you can see what Mona Lisa looks like on this one. And as far as I know, right now I don't know of a better way to produce Mona Lisa on a laser printer, on the kind of a machine that Apple Laser Writer or Imogen or HP laser writer all use the same engine. So this actually made a rather attractive thing. The way I did this is a little bit fun. I don't have control of the software where I can turn on every bit of the laser printer, and if I send it one bit at a time on a font that would just be very small, this would come in too slow for the software, and I would get all kinds of streaks on the page. And so instead, I had to make this as a font of 64 characters, where each character covers a small part of Mona Lisa. And so this picture was actually typeset as a combination of these 64 characters. And once you got something like that, then you can play games like this. And now in this one, I took each of those 64 characters, repeated it 4 times. So you have sort of 0, 0. Each column is repeated twice, and each row is repeated twice. But you don't see the joins between, because 2 matches perfectly to 3. And so although it goes 0, 0, 1, 1, 2, 2, 3, 3, you actually see 0, and then you see 0, 1 as a glot, and then you see 1, 2 as a glot, because there's no boundary between 1 and 2 visible. This is something that Leonardo, I'm sure, would have been excited about. All right. Now I tried it on another image, and this one I generated completely by computer, and this points out the Achilles heel of these methods. In fact, so here I just generated a sphere and some background that was gradually getting darker, and this with the Floyd-Steinberg method. There tends to be a problem when it goes through 1/2. Here's the area of 1/2 where there tends to be a band around there where it drops out, and then there's also various stripes that occur. These artifacts of texture that seem to just be, unfortunately, because of number theory, that they happen because when we're applying this method. But you notice the enhanced contrast has an interesting feature, how it puts a white stripe outside the sphere as well as a black stripe in the sphere. The ordered dither looks like this, my dot diffusion method looks like this. Now here's where I had a problem that I didn't anticipate. So as far as I was concerned, my method was a winner for laser printers, and I had high hopes that it would work also when I increased the resolution for phototypesetter. But now on this one, something else is going on. So I've got right average values, but unfortunately when you step back and reduce this down, then there's some false contour introduced here where I'm changing, where the picture is actually just changing gradually, getting a little grayer, but the pattern of black and white that I choose is not changing gradually. The pattern I'm choosing is, since it's done by this error, these errors are propagating in slightly different ways, I get the same average number of black dots, but they're occurring in a different configuration. And this is tending to make a little band in there that's probably going to be all too visible, while there shouldn't be any band at all because nothing is going on in that part of the picture. So I need something else in order to, before I can claim that this is going to be an exciting method. Okay, now the referees of my paper pointed to two recent pieces of work, and I want to tell you about those because I want to try this stuff as soon as I get back home. So people have made two important other nice ideas I didn't know about until just last week, and worthy of further exploitation. First of all, somebody noticed that this constant 1/2 here isn't important. That is, I could try this Floyd-Steinberg method, but instead of 1/2, suppose I made it 3/4. At first, that seems ridiculous. I mean, you have to, half the time you have to go to 0, and the other half the time you have to go to 1. But suppose this was really 3/4. Well, what's happening is that you very often set the thing to 0 at this point, but you're making a bigger error. So this error is immediately being spread to the next thing, and it'll bias your decision. And we know that this method is distributing the errors, and so it's still going to come out with the same average. So no matter what this threshold is in here, I'm getting a method that diffuses the error and comes up with the average properties. So these two men in the physics department in Germany who observed this, they decided that they would combine this with the method of ordered dither, and they would choose a different threshold at every I and j, and this I and j threshold would form some other pattern that would tend to knock out the improper texture that sometimes is supplied by this Floyd-Steinberg method. And in their experiments, they got the best results when they were choosing the extra thresholds to form a pattern something like dots, not according to ordered dither, which kept the dots apart, but according to a method where the clusters there are some parts of it that are arranged like in a 45-degree grid, where those dots would be were the ones that have the highest threshold, and then the other parts, the white dots, the complement of the black dots, would be the ones that have a lower threshold. But then this would tend to, then the threshold, they were varying it not between 0 and 1, but between, I think it was 2/10 and 8/10 at these points, and they were getting an error diffusion method that was free of much more free of these false contours. That was one neat idea that I found in the literature. The other one was actually somewhat older and developed at Xerox in the late 70s. It's called the Aries Method, and here what they did was something like the ordered dither approach, except that they would take a say an 8x8 region of the picture, and they would apply the ordered dither method, but they would change the threshold in that picture to be just right, so that the total number of blacks in that picture would be what you wanted. So let me explain this a little bit. You got an area of say 64 pixels, and you add together all the A values in those 64 areas, and it says that it would be nice if I could turn on 13 of those 64 pixels. Okay, so now which 13 should I choose? What they say is take some dither matrix, and so Aij plus Dij, and look at those 64 values. take the 13 highest values and make those 1. And now this has the properties that, well, now you can choose a dither matrix so that these values will group themselves nicely for printing ink. So they got rather good results with that. Now what I hope to find when I get back to Stanford next week is that I can actually use both of these methods, and that is I can, both of these ideas somehow that I, well, no, the second idea is too computationally expensive. I would like to try to use the first idea, changing the threshold, combine that with my method, and then see if that doesn't produce results that are as good as or better as this Aries method. Who knows? For laser printers, the right solution might not be the one that's going to be best for higher resolution printing. And the only way to really judge this will be to have some method that doesn't just compare the average values of the BIJs to the average of the AIJs, but to have something that compares the perception as seen by a human being of the AIJs to the perception as seen by a human being of the BIJs, and that's not simply an average. In fact, it's not only due to the things that are the properties of our eye, the way our eye works and perceives patterns, but it's also due to the properties of the printing press and the way ink changes. One of the big problems with the ordered dither method and Floyd-Steinberg method is if you have a picture that's entirely 1/2, all the AIJs are 1/2, these will give you a checkerboard, a perfect black, white, black, white. Now this is the absolute worst thing to put on a printing press. You can't put dots of ink at the points of a checkerboard and not dots of ink there. It just all blurs together and makes blotches. You have to have larger dots than that because these little pixels are terribly small on the print. So we need a combination of a model of what the printing is going to do, what our eyes are going to do, and then try to see what's going to come out to be a good image after all of that. Now our eyes are very good at picking up differences between areas. Not so good. So our eyes aren't so well tuned to absolute darkness. We don't know the difference between 1/3 and 1/4 when they're in the middle of a picture. But when you put a 1/3 next to 1/4, we see an edge between. This is, and I have an interesting. I just stumbled on an interesting demonstration of this when I was playing around with my fonts for Halftones. I decided, what if I had a font where I would have 65 characters for 65 levels of brightness, but I would make each of these characters equally black. So there would be no difference between the black one and the white one. But the only difference I decided I was going to consider that I had the needles on a dial, and if the needle is flat, this means it's the A value is 0. If the needle is straight up, the A value is 1. And if the needle, if A value is 1/3, the needle goes up 1/3 of the way. So you can imagine that you have a lot of photoelectric cells or something attached to needles, and you shine a picture on there, and you see the needles turn. Can you see what the picture is? Well, in fact, of course, you knew what this picture was. You had already seen it. But how about this one? Can you guess what this picture is? Now every pixel in this picture has exactly the same black-white density. There's nothing darker about than any other. But the fact that we can see the difference between when the needles move, that's where we're picking up the texture. And so I guess I thought I'd end my talk on a patriotic note by showing you this. I have one more example if I can find it. Yeah, where instead of using dials, I just took horizontal and vertical lines, and I moved to the left or to the right and up at the same time. So here I have two crosshairs, and this is for 0 and this is for 1, and everything in between is shown here. So amazingly easy to perceive, although there's no difference in brightness because of the way our eye focuses on differences. So I guess the summary of the talk is that we start out. We still have a fascinating problem, I think, is find out what pattern of bees will actually be the best for printing. Is it really going to be true that nobody can do better than the analog methods that were discovered years before computers come along, or can we find patterns that will actually make Ansel Adams look even better, look like the real prints instead of the way they look in books? Our book's going to be able to be improved even more if we come up with the right patterns. Okay, that's my talk. Any questions?
Questions?
Yep.
You said if you have a randomized picture, you notice rivers black and white because while true the global average is bright, the local average makes it higher to glow. What happens if you try using halftones by first using randomization to check, whereas the higher the intensity, the more probable it is to turn the right color, whatever white or black notation you use. But
Yeah.
the second pass where you kind of then use your error correction to.
Now your first one you said randomization, but then you said use high intensity.
Well, I'm saying
So
randomization would say that the higher the intensity is supposed to be, the more likely it is that you get
yeah. Well, in fact,
randomization is the first pass, but then the second pass to correct your local error.
yeah, this was in fact the idea that I had written and got almost ready to test, and then I decided that this dot diffusion method was going to be better, so I threw it in the wastebasket. Maybe I should try it again. But I went through the whole matrix and I tried to find first of all the pixel that was whose decision was most obvious. I mean, like, you know, the A that's closest to 0 or to 1. So I kept a big priority queue of all the pixels, and there were millions of them, of course. So I only worked on a band. So I say, you know, look at the top 16 rows or something by 350 or whatever I had. It still was a very small segment of the picture. But I said, now put those all into a rate those all by how controversial the decision is there, and then choose that, you know, choose the one that's the least controversial, and then propagate the error to its neighbors and recalculate the same thing again, and keep on going until I get to the end. Okay, so that method was one that I had planned to, and I had actually implemented the data structures and everything, and I never did test it. But now I suspect that that's not going to that's going to suffer from the same banding problem that I showed you on this sphere. And one way to see that is if you have any method that's going in that, well, you suppose you have something that's going gradually from light gray to dark gray. We have to see something that changes very gradually. Now if there's any interaction between these, we'll see an artificial contour in between. And one of the ways to imagine this is, suppose that I'm calculating something where the gray level is very close to 1/2. I mean, this is almost too dramatic. But suppose the gray level is very close to 1/2, and in the left half of the picture, I'm computing it so that it's so close to 1/2 that it really comes out to be a checkerboard, black-white. And on the other half of the picture, it's also close to 1/2. But on the other side, but somehow I got a little bit more than 1/2. So my checkerboard isn't black-white; it's white-black. So now I have these two parts, and both of them are locally 1/2. But there's got to be a place in there where they meet each other, and there's going to be a big stripe, and that's going to appear. And so some method that avoids any such stripes like that is absolutely essential to avoid artificial contours. That's why I like the Aries method. Seems to be quite free of that, and I suspect that might be the best we can do at the moment. But I still want to do some more trial. When I say best, I mean on a really high high-resolution printer. Yeah. No? Yes?
How important is it to correct all the errors in the picture? All the methods you said that the last pixel gets all the errors.
Right. Yeah.
It seems to have been the pixels that have been the longest.
That's right. Yeah, I know. That's another thing that would be worth keeping track of all the errors. This is the kind of mistake a mathematician tends to make, and we have to in computer science we have to try first for a clean model, but we have to realize that mathematically clean doesn't necessarily mean best in the real world, and so we have to be willing to reject that and take something something else. We try to find the cleanest one that actually works, but we don't stop searching just because none of the clean ones work. But we should stop. But our weakness is that we sometimes stop searching when there is a clean one because we are tolerant enough of the unclean. Well, where was I? So you're absolutely right. We could, for example, say that if we have a small error, we won't distribute it at all, or we could say that we only distribute a certain percentage of the error. Or we could, but something probably the error could go a little ways. Now, this method that they use for the picture of me that I showed you there might be a good example of that. They keep two matrices. They keep the original Aij and the one subject to error modification. So the errors that they compute are based on the difference between original A and computed B, while in the Floyd-Steinberg method, the errors are modified A versus computed B, so that the error there is I mean, you see what I mean? In Floyd-Steinberg method, we update the A matrix as we go along, so we're dealing with different A's. But in this other method, the A matrix stays the same, but the errors are still kept track of the original A versus the computed B. So it takes more memory, but it might remove some of this effect of being too anxious to save every little twiddle of error. The history of computer science is full of examples where somebody has optimized by one criterion and then other criteria have gone by the wayside. Order dither is one example of this, where by one criterion the matrix that I showed you for order dither, the 0 to 63, was the optimum one. But when you try to apply that to high-resolution printing, it turns out to be very bad because the 50% tone would come out to a checkerboard, which would look terrible on a printing press. The same thing if I tried to use the ordered dither matrix for my diffusion method. There I would have as many barons as possible. There would be, I'd be eating error in all different ways. On the other hand, if I take my criterion as to try to minimize the total amount of escaped error, then I might be losing on some other visual grounds, and the extra stripe that occurred in the background of the sphere was an example of that. Yes.
A picture of a regular printer with a halftone, the same kind of resolution.
Yeah, I ought to have that for comparison, but I don't control a printing. In other words, I tried to go through the graphic arts department to get some things like this, and found out that it was just the printers weren't able to make two things that would be under the same assumptions when one of the assumptions was old and the other was new. Okay, because they understood the old, but they wouldn't be able to adapt to the new, so they would tune them up so that they would come out the same, or they would play games. Because the fact is that they also have a lot of dials on the printing presses that adjust the ink and so on. And one of the worst failure I had was I had these three methods. brand X, brand Y, and my method on the spheres. And let's see, here it is. Well, we can't see it. Actually, because this is already reduced on a Xerox, a lot of the thing goes away. But the fact is, when you try to make a what kind of print is this, a PMT print, and you with a reducing machine, and try to reduce this by a factor of 10. You still have a control on the exposure as to how long you keep on the light as you're making these prints. And so I said, well, I'd like to compare these three methods, the brand X, brand Y, and this one. And no matter what they would do, these would turn out to be much darker than this. Okay, so my idea was to make this one look good, and these other ones would look way too dark. See, but their idea was to make 2 out of, best if they would get 2 out of 3 anyway. Or they would say, can I do this one with a different exposure? And so then I tried to imagine what would happen after I took such a photograph and sent it to ACM's printer, and that they would reproduce it in the journal and so on. And we would get something that would be impossible to evaluate. So I have no way of really evaluating these things well, except by not, I can't. This Xerox copy I'm making now has already been quite distorted because of the xerography. But I can show you a hard copy on laser printer output, and that's in which the subjective judgment is finally made that I did like this method in 1K. The main point here I want to say is it's still a problem, and some more ideas are clearly possible. This is very much in its infancy, even though there's already a literature of about 100 papers on the subject.
Let me suggest that we stop now, but those of you who'd like to continue with questions, discussion, come forward. Thank you very much.
Hard copy.